So far, we've talked about two forms of encryption, symmetric and asymmetric. In this next lesson, we're going to cover a special type of function that's widely used in computing and especially within security, hashing. No, not the breakfast kind, although those are delicious. Hashing, or a hash function, is a type of function or operation that takes in an arbitrary data input and maps it to an output of a fixed size, called a hash or a digest. The output size is usually specified in bits of data and is often included in the hashing function name. What this means exactly is that you feed in any amount of data into a hash function and the resulting output will always be the same size, but the output should be unique to the input, such that two different inputs should never yield the same output. Hash functions have a large number of applications in computing in general, typically used to uniquely identify data. You may have heard the term hash table before in context of software engineering. This is a type of data structure that uses hashes to accelerate data lookups. Hashing can also be used to identify duplicate data sets in databases or archives to speed up searching of tables or to remove duplicate data to save space. Depending on the application, there are various properties that may be desired, and a variety of hashing functions exist for various applications. We're primarily concerned with cryptographic hash functions, which are used for various applications like authentication, message integrity, fingerprinting, data corruption detection, and digital signatures. Cryptographic hashing is distinctly different from encryption because cryptographic hash functions should be one-directional. They're similar in that you can input plain text into the hash function and get output that's unintelligible, but you can't take the hash output and recover the plain text. The ideal cryptographic hash function should be deterministic, meaning that the same input value should always return the same hash value. The function should be quick to compute and be efficient. It should be infeasible to reverse the function and recover the plain text from the hash digest. A small change in the input should result in a change in the output so that there is no correlation between the change in the input and the resulting change in the output. Finally, the function should not allow for hash collisions, meaning two different inputs mapping to the same output. Cryptographic hash functions are very similar to symmetric key block ciphers in that they operate on blocks of data. In fact, many popular hash functions are actually based on modified block ciphers. Let's take a basic example to quickly demonstrate how a hash function works. We'll use an imaginary hash function for demonstration purposes. Let's say we have an input string of hello world and we feed this into a hash function which generates the resulting hash of E49A00FF. Every time we feed this string into our function, we get the same hash digest output. Now let's modify the input very slightly so it becomes hello world, all lowercase now. While this change seems small to us, the resulting hash output is wildly different, FF1832AE. Here is the same example, but using a real hash function, in this case, MD5sum. Hopefully, the concept of hash functions makes sense to you now. In the next section, we will explore some examples of hashing algorithms and dive into weaknesses or attacks on hash functions.